6. In figure 16.8, all possible distributions and microstates are shown for 4 different particles shared between 2 boxes. Determine the entropy change, which is delta S, if the particles are initially evenly distributed between the 2 boxes, but upon redistribution, they all end up in box B. Okay, so we have to find out the entropy change from different microstates. Now, I did put up figure 16.8 here, which we will be, pulling our answer from here. But just know that, entropy is always talking about randomness of molecules. It's basically, in this case with microstates, it's all about probability. What's the probability of these 4 different colored, balls end up in the 2 different boxes? Now, we just have to find that delta S, right, the entropy change, upon what they told us. So when we're talking about microstates and delta S, there's only one formula, and that's the formula right here. It's delta S equals K, ln of WF divided by WI. Now, we're trying to solve for the delta S, right? That's the entropy change. K is a constant. This is the Boltzmann constant. So, thank goodness for that. This is 1.38 times 10 to the negative 23rd. And the units, if you really wanted to know the units, this would be joules per Kelvin. And that's why the delta S units are also standard joule per Kelvin for this formula. So the Boltzmann constant K and your delta S values have the same units, mainly because your W values have no units, so they're unitless. Now, what is a W? Well, the W's are your number of microstates. And it's F, which is final, so the number of microstates final divided by the number of microstates initial. But now we just got to find out what those numbers are. Well, let's just plug in what we know so far. Delta S equals the Boltzmann constant, which is 1.38 times 10 to the negative 23rd. And now we're just going to take the ln of something divided by something else. Well, let's see what our initial is, right? They said that these particles were initially evenly distributed between 2 boxes. So if we have, in all of these, we have a total of 4 balls, right? And we are evenly distributed between the 2 boxes. Do you know how many balls are in each box? Yeah, that means that there's 2 balls per box, right? We're looking for something that has the same number. It's evenly distributed between the 2 boxes. So in this case, we're looking for 2 balls in 2 boxes. Or we'll say 2 balls in each box. So I'm just going to go through all my microstates and pick out which ones fit the bill. So this one, no, right? I'm looking for 2 on each box. So this is like 3 and 1, 3 and 1. But when I come down here, 2 and 2. So this checks out. This checks out, 2 and 2. Here's another one, 2 and 2. 2 and 2, 2 and 2, and 2 and 2. Just going to make sure if we look at D, no more 2 and 2. They're not evenly distributed. So how many total microstates are here? There's 6, right? So that would be our initial value. It would be a 6. There were 6 initial microstates that, they were describing. Now we just have to find out the final microstate, right? Or how many total microstates are in the final, scenario here. Well, they did tell us that upon redistribution, right? Upon redistribution, they're talking about final. And upon redistribution, they all end up in box B. Now, I do look at B here, and there are technically 4 different boxes. However, they're being very specific. They're just saying that all of them are ending up in a box. This is singular. We're not ending up in boxes, right? You see how over here it says just 2 boxes? But now they're all ending up in box B. So I got to look for box B. Now, let's just say that the first box is labeled as A, and the second box is labeled as B. So for all of these, we have A and B, A and B, A and B, etc., right? So if all of them are just ending up in box B, we're not really looking here. We're looking for the one in which all the balls are in this final box. And that is down here. This is the one they're really talking about, where all of them are ending up in box B. How many microstates is that? That's just one of them. So this would just be a 1. So now it's just calculator time, right? I'm going to do this all in one shot. You can take the ln of 1 over 6 and then multiply it by the Boltzmann constant. I believe in you guys. Let's see if we get the same answer. So ln 1 over 6 and then times it by 1.38 times 10 to the negative 23rd. And I get, no sig figs. So I guess we'll do 3. Negative 2.47 times 10 to the negative 23rd. And remember, those units are joules per Kelvin. And that is your enthalpy change. And in this case, the enthalpy change is a negative value. Any delta S value that's a negative value, that means you went from something that was more random, more choices, to something that only had one choice. You went from something from more randomness to less randomness. That's always a delta S of a negative value. And there you go. I really hope this one helped you out. Let me know in the comments. Subscribe to the channel, and I look forward to helping you with future questions. I will talk to you soon. Okay, bye-bye.